Right now, the Andromeda Galaxy is falling toward you. Not metaphorically, not in some poetic sense that dissolves under scrutiny. Measured, confirmed, calculated from decades of data gathered by some of the most sensitive instruments human beings have ever constructed. Right now, as you lie here, as the room sits quiet around you, as whatever was occupying your mind before you press play continues its slow orbit somewhere in the back of your thoughts, a galaxy containing 1 trillion stars is moving through space on a direct collision course with the one you live in. The speed is 110 kilometers per second. Every single second, it closes the gap by 110 kilometers. In the time it takes you to hear that sentence, Andromeda has moved roughly 330 kilometers closer to us. That is the distance between London and Edinburgh, covered in 3 seconds, by something that contains more stars than there are grains of sand on every beach on Earth, moving through ancient empty space at a speed that makes every human concept of fast feel inadequate. You feel nothing. The room is still. Your body registers none of it. The phone in your hand sits undisturbed. There is no vibration, no signal, no sensation that would allow a human nervous system to register what is happening at this scale. And yet, it is happening. This is not speculation. This is what the data says. Multiple independent teams, multiple instruments, multiple decades of observation, all converging on the same answer. Before we go any further, the background you may be watching right now has nothing to do with what I am about to tell you. That is always how we do it here. If you want to close your eyes, put the phone face down on the pillow. Let the darkness be dark and let this voice carry you where it goes. Do that. This is built to be listened to in the dark. It is made for the space between waking and sleep, for the brain that needs something to follow that is bigger and stranger than its own worries. Get comfortable, because this story is going to take a while. It goes much deeper than a collision. This is the full story. Every layer of it. The timeline, the physics, the consequences that most explanations gloss over or never reach, and the question at the end that most people never think to ask. By the time we are done, you will not just understand what is going to happen to the Milky Way. You will understand what it means for the galaxy, for the stars, for the black holes at the center of everything, for anything that might still exist and still be capable of looking up when the final stages play out. If deep investigations like this are what you come here for, subscribe before we go further. The next one is already being built. The investigation begins now. Let's start with a smudge of light. 2.5 million light-years away in the constellation Andromeda, there is something visible to the naked eye on a clear night, far from the contamination of city lights. It is a soft, diffuse patch of luminosity, roughly 6 times the apparent width of a full moon in the sky, though most of that extent is too faint to see without instruments. It has been noted by astronomers for at least 1,000 years. The Persian astronomer Abd al-Rahman al-Sufi described it in the year 964 AD as a small cloud. The name persisted for centuries because a cloud is precisely what it looks like to an unaided eye on a dark hillside. They were wrong about what it was, but they were right to pay attention. In 1923, Edwin Hubble pointed the 100-inch Hooker telescope at Mount Wilson Observatory in California toward that smudge and began looking for something specific inside it. He was looking for Cepheid variable stars. These are stars that pulse in brightness at a regular, repeating period, and whose period is directly tied to their intrinsic luminosity. The relationship was discovered by astronomer Henrietta Swan Leavitt in 1908, working from photographic plates at the Harvard Observatory, studying the Cepheid population of the Magellanic Clouds. She noticed that the brighter Cepheids had longer periods. The pattern held precisely across a large sample. It held because it reflects something real about the internal physics of these stars. The balance between gravity pulling inward and radiation pressure pushing outward, cycling in a way that is governed by the star's actual luminosity. What this means in practice is this: if you can measure the pulsation period of a Cepheid variable, you know how bright it actually is. If you know how bright it actually is, and you can measure how bright it appears from where you are, the distance follows directly from the way brightness fades with distance. You do not need to measure the distance directly. You calculate it from the light. The math is not complicated. The implications were world-altering. Hubble found Cepheid variables inside the Andromeda smudge. He measured their periods. He used Leavitt's calibration to determine their intrinsic luminosities. He measured their apparent brightnesses from Mount Wilson, and then he calculated the distance. The number that emerged was incompatible with Andromeda being a cloud inside the Milky Way, or anywhere inside the Milky Way, or even within a distance that made it part of our galaxy in any meaningful sense. His initial estimate was approximately 900,000 light-years, a significant underestimate because the calibration of Cepheid distances available to him in 1923 contained a systematic error that would not be corrected for decades. The true distance is 2.5 million light-years, but even the underestimate was decisive. Andromeda was not a cloud. It was a galaxy, a separate island of hundreds of billions of stars, existing at a distance so vast that the light arriving from it tonight left before the first humans walked upright on this planet, not before recorded history, before our species. The universe was not just the Milky Way surrounded by a modest scattering of clusters and clouds. The Milky Way was one island in an ocean of islands, stretching in every direction across distances that made the Milky Way itself look provincial. The great debate that had divided astronomers through the early 20th century, were the spiral nebulae inside our galaxy or beyond it, was resolved. And the resolution favoured the more extreme of the two options, not just outside our galaxy, unreachably far outside it. In its own territory, across a gap so large that only the specific trick of Cepheid variables could bridge it. The second shock came when people began to ask not just where Andromeda was, but where it was going. Measuring the motion of a distant galaxy requires detecting a Doppler shift in its light. The Doppler effect is the same phenomenon that makes a siren change pitch as an ambulance passes you on a street. When a sound source moves toward you, the sound waves are compressed and the pitch rises. When it moves away, the waves stretch and the pitch falls. Light behaves the same way. A galaxy moving away from you will have its spectrum shifted toward longer wavelengths, redshifted. A galaxy moving toward you will be shifted toward shorter wavelengths, blue shifted. Most galaxies in the universe are redshifted. They are moving away from us, not because they are actively fleeing, but because space itself is expanding and carrying them. Every galaxy group is carried away from every other galaxy group as the universe grows. This was first established systematically by Hubble in 1929, when he plotted galaxy distances against their recession velocities and found a linear relationship. The further a galaxy, the faster it receded. The universe was not static, it was growing. But Andromeda is not redshifted. It is blue shifted. Its light arrives at our instruments compressed, not stretched. Andromeda is moving toward us. This has been confirmed by many independent measurements across many decades. The blue shift is not ambiguous. The direction of motion is not in question. What was in question for a long time was the precise three-dimensional direction of that motion. A blue shift tells you only the component of velocity aimed along your line of sight, the speed at which something is approaching or receding in the direction you are looking. It tells you nothing about lateral velocity, the component of motion perpendicular to your line of sight, the degree to which the object is also moving sideways across the sky. And lateral velocity matters enormously when you want to know whether two objects will collide or miss each other. If you see a car approaching you and you only know how fast it is coming, you do not know whether you are in its path. You also need to know where it is aimed. Measuring Andromeda's lateral velocity requires tracking the actual positional shift of the galaxy across the sky as it moves. At a distance of 2.5 million light-years, even a lateral velocity of several hundred kilometers per second produces an angular motion of micro-arc seconds per year, millionths of a degree. This was below the detection threshold of every instrument available for most of the 20th century. In 2012, a team led by astronomer Roland van der Marel published the first reliable measurement of this motion using the Hubble Space Telescope's fine guidance sensors. Instruments designed for pointing control, but sensitive enough to detect positional shifts that no ground-based observatory could resolve. The team tracked individual stars inside Andromeda across multiple years of observation, measuring the tiny angular shifts that indicated the direction and magnitude of the galaxy's sideways motion. The result, the lateral velocity of Andromeda, is low, much lower than the line of sight approach speed. Low enough that when you combine both components, the trajectory of Andromeda points essentially at us. The two galaxies will not miss each other. They are on a collision course. The paper was peer-reviewed. The data were unambiguous. Subsequent work using Gaia satellite data has refined the estimate without overturning it. The first close encounter, approximately 4.5 billion years from now. Hold that number. The Sun is approximately 4.6 billion years old. The Earth is 4.5 billion years old. In roughly the same span of time that has already elapsed since the formation of this planet, the Milky Way and Andromeda will be close enough to have begun their mutual destruction and transformation. The timeline is not geological, it is cosmological, and the universe has scheduled this event at a distance from the present that mirrors Earth's entire history with an unsettling precision. Now let's talk about what a galactic collision actually is, because the word collision almost certainly conjures an image that is completely wrong. When people hear that two galaxies are going to collide, they picture dense clouds of stars crashing together, an impact, a catastrophe, heat and light, and the annihilation of structure. If that image is in your head, release it. The reality requires thinking seriously about emptiness. A galaxy is not a dense object. It is extraordinarily sparse. The Milky Way contains somewhere between 200 and 400 billion stars distributed across a disk roughly 100,000 light-years in diameter and a few thousand light-years thick. The average distance between neighboring stars is approximately 4 to 5 light-years. That is the distance light travels in 4 to 5 years, at 300,000 kilometers per second. To feel what that means, imagine shrinking the Milky Way down to the size of the North American continent and representing each star as a grain of sand, roughly 1 millimeter across. Those grains of sand would need to be separated from each other by approximately 5 kilometers each. 5 kilometers of nothing between each millimeter of star. The model would be 500,000 kilometers across, larger than the Moon's orbit around Earth. That is what a galaxy actually is, a near vacuum populated by isolated points of light, separated by chasms of cold and dark so large that the concept of distance barely functions at human scales. When two such near vacuums interpenetrate, the probability that any given star directly collides with another star is effectively zero. Not negligible, effectively zero. The Milky Way has hundreds of billions of stars. Andromeda has hundreds of billions of stars. During the entire merger process, several billion years of the two galaxies passing through and around each other, the expected number of direct stellar collisions is close to none. The stars will pass through each other like two swarms of fireflies merging in the dark. They will be deflected by each other's gravity, thrown into new orbits, scattered from where they began, but they will not hit. What does collide? What has no mechanism for passing through anything? Is the gas. Between the stars in both galaxies lie vast clouds of molecular hydrogen, helium, carbon monoxide, and heavier elements seeded by stellar evolution. These clouds are the raw material for star formation. They are cold, dense by interstellar standards, and held in rough equilibrium between their own self-gravity and the internal turbulence and radiation that prevents them from collapsing. The Milky Way contains hundreds of giant molecular clouds, each spanning hundreds of light years, each with enough mass to birth hundreds of thousands of new stars if compressed correctly. Gas clouds do not pass through each other. When two galaxies interpenetrate, these clouds slam together at the relative velocity of the merger, in our case, over 100 kilometers per second. The collision sends shock waves through the clouds. Temperatures spike. Pressures build. The gas cools rapidly after the shock passes, but it is now denser and more gravitationally unstable than it was before. Dense cores form within the compressed gas. Those cores collapse. Stars ignite, not one at a time, as in the quiet, steady star formation of an undisturbed galaxy, but in simultaneous bursts, hundreds of thousands of stars at once. This is called a starburst, and it is one of the most energetically spectacular processes in the universe. We have not just modeled this, we have watched it happen. The antennae galaxies, catalogued as NGC4038 and NGC4039, approximately 45 million light-years away in the constellation Corvus, are two spiral galaxies in the middle of a collision that began roughly 40 million years ago. In the overlap region, where their gas clouds have been compressed, star formation is proceeding at a rate hundreds of times higher than in a normal, undisturbed spiral galaxy. Hubble Space Telescope images of the antennae show thousands of young star clusters blazing blue against the background of disturbed stars. Concentrations of massive, hot, short-lived stars born from the compressed gas within the past few million years. Long, tidal tails of stars stripped from both galaxies by gravitational forces during the initial encounter extend for hundreds of thousands of light-years into surrounding space. The two nuclei are still distinct but converging. The antennae provide direct observational confirmation of the starburst mechanism. They are not a theoretical prediction. They are a photograph of a process that is already underway, at a stage we expect our own collision to resemble in a few billion years. Now let's walk through the merger timeline as the computer models describe it. These models are not guesswork. They are constrained by real measurements of both galaxies, their masses, their dark matter halo profiles, their velocity dispersions, the measured approach velocity and lateral velocity of Andromeda. They are validated against observed merging systems like the antennae and dozens of other galaxy pairs at various stages of interaction. Multiple independent groups have run these simulations using different codes and different parameter sets, and they converge on a consistent picture. The uncertainties are in the timing, hundreds of millions of years here or there, not in the qualitative outcome. Approximately 3.75 billion years from now, Andromeda will be visibly large in the night sky. No longer the faint smudge requiring dark skies and patience, but a broad structure spreading across a significant arc of sky. Its central region will be bright enough to be conspicuous even from lit environments. The outer disk will cover many degrees. The Milky Way will also look different. The mutual gravitational influence is already beginning to distort both systems, and the tidal material drawn out from each galaxy will be visible as enhanced structure. If Earth still exists and anyone can see the sky, they will be living under a night that looks nothing like ours. Approximately 4.5 billion years from now, the first encounter. The outer regions of both galaxies begin to interpenetrate. The disk of the Milky Way, the flat, organized plane of stellar rotation that defines our galaxy's spiral character, begins to warp under Andromeda's tidal influence. Tidal tails of stars are drawn out from both systems, long filaments of displaced stars stretching hundreds of thousands of light years into surrounding space. The first starburst ignites in the compressed gas at the intersection of the two systems. Millions of new stars are born over a period of tens of millions of years. After the first pass, the two galaxies do not simply continue on separate paths. The encounter has cost them kinetic energy through dynamical friction. The gravitational drag experienced by a massive object moving through a field of lighter objects, which creates a slight concentration of mass behind the moving object that pulls it backward. Over millions of years, this drag slows both galaxies relative to each other, transferring kinetic energy into the internal motions of the stellar populations. The separation that follows the first pass is temporary. Both galaxies are now gravitationally bound to each other in a way they were not before. The gap reopens, reaches a maximum, and begins to close again. Approximately 5.1 billion years from now, the second close encounter. The galaxies swing through each other again. More starburst, more tidal disruption. The organized spiral structure of the Milky Way is increasingly dissolved. The coherent rotation of the disk, the defined arms, the bar at the center. These structures depend on the organized angular momentum of a disk, and that organization is being progressively scrambled by the gravitational influence of Andromeda's passing stellar population. Between 6 and 7 billion years from now, the final coalescence. The two nuclei converge. Stars from both are scattered by gravitational slingshot interactions into wide, randomized orbits. The remaining gas, funneled inward by the collapse of the overall mass distribution, feeds one final starburst and begins to fall toward the central black holes. Over hundreds of millions of years, the combined system settles into the lowest energy configuration available to it. What emerges is an elliptical galaxy, a roughly spherical or ellipsoidal distribution of stars with no preferred plane of rotation. No spiral arms, no organized disk, very little remaining gas for new star formation. The starbursts have consumed it. What remains is an old stellar population punctuated by the younger stars born during the merger, a mixed community of ages and metallicities, orbiting the combined gravitational center from every direction. Astronomers call the product Milkomeda. It will contain most of the stars from both original galaxies. It will be physically larger than either parent. And it will be old, growing older, its starbursts completed, its gas exhausted. Now let's talk about dark matter, because we cannot tell this story properly without it. Neither the Milky Way nor Andromeda are entirely made of the stars and gas you can see. Most of the mass of each galaxy is invisible. It does not emit light. It does not interact with electromagnetic radiation in any way that current instruments can detect. We know it is there only through its gravitational effects, its influence on the motions of the stars and gas that we can see. This is dark matter. It was first inferred in the 1930s by astronomer Fritz Zwicky, who measured the velocities of galaxies in the Coma cluster and found they were moving far too fast to be held together by the visible mass of the cluster. The cluster should have flown apart long ago if the only mass present was the mass we could see. Something invisible was providing additional gravitational binding. Zwicky called it Dunkle Materie, dark matter. The evidence became overwhelming in the 1970s and 1980s when astronomer Vera Rubin and her collaborators measured the rotation curves of spiral galaxies, the relationship between orbital speed and distance from the galactic center. In a system where most of the mass is concentrated in the visible disk and central bulge, you would expect orbital speeds to decline with distance from the center, just as the planets in the outer solar system orbit the Sun more slowly than those in the inner system. Instead, the rotation curves of spiral galaxies are flat. Stars at the outer edge of the disk orbit at roughly the same speed as stars much closer to the center. The only explanation consistent with this is that each galaxy is embedded in a much larger, roughly spherical halo of mass, invisible mass, that extends far beyond the visible disk and provides the additional gravitational influence needed to sustain the high orbital speeds at large radii. The dark matter halo of the Milky Way is roughly 10 times the total mass of all the visible stars and gas combined. The same is true for Andromeda. When two galaxies merge, it is not just the visible components, the stars and gas, that are interacting. The dark matter halos are interpenetrating as well. In fact, the halos of the Milky Way and Andromeda are probably already overlapping at the fringes, given their sizes and the current separation between the galaxies. Dark matter does not collide the way gas does. Dark matter particles, whatever they are, and we do not know, do not interact with each other through the electromagnetic force. They interact only through gravity. So dark matter halos pass through each other much the way the stars do, not compressing or shocking, but exchanging gravitational energy and gradually being drawn into the combined potential well of the merger. The final merged dark matter halo of Milkomeda will be significantly larger and more massive than either parent halo. This matters for the structure of the merger. The dark matter halos provide the gravitational scaffolding within which the visible components, the stars and gas, are embedded. The dynamics of the merger depend on the dark matter profile as much as on the visible mass distribution. The simulations that predict the merger timeline are simulations of total mass, including the dark matter, not just the visible components. Without dark matter, the predictions would be different. What dark matter is made of remains unknown. Particle physicists and cosmologists have proposed many candidates: weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and others. None have been definitively detected. the Large Hadron Collider at CERN, which reached energies sufficient to produce the Higgs boson, has not produced a dark matter candidate. Underground detectors designed to catch dark matter particles passing through the Earth have found nothing beyond background. The evidence that dark matter exists is overwhelming. The evidence for what it actually is remains absent. This is not a small gap in knowledge. Dark matter makes up approximately 27% of the total energy content of the universe. Combined with dark energy at 68%, the two unknown components together constitute roughly 95% of what the universe is made of. The ordinary matter, protons, neutrons, electrons, the stuff that forms stars and planets and people, is approximately 5% of the universe by energy content. We understand 5% of what the universe is made of well enough to describe it from first principles. The rest is confirmed to exist and almost entirely unexplained. Keep that in mind as you listen to confident statements about how the merger will unfold. We know the merger will happen. We know the timeline with reasonable precision. We know the qualitative outcome. And we know that most of the mass involved in the process is something we cannot identify, detect directly, or explain from known physics. The universe is legible in parts. It is opaque in others. The collision of the Milky Way and Andromeda is a story about both. Now let's go to the black holes, because this is where the story changes character most dramatically. At the center of the Milky Way, 26,000 light-years away, there is a supermassive black hole called Sagittarius A star. Its mass is approximately 4 million times the mass of the Sun. We know it is there because we have spent decades tracking the orbits of individual stars near the galactic center, and those orbits obey Kepler's laws around an invisible point of enormous mass. The most studied of these stars, designated S2, has been observed through a complete orbital period of approximately 16 years. Its orbit is elliptical with a high eccentricity. At its closest approach to the center, S2 moves at nearly 3% of the speed of light. The gravitational mass producing this motion, calculated directly from the orbital parameters, is 4 million solar masses. There is no configuration of visible matter that could account for this. A supermassive black hole is the only candidate consistent with the observations. This is established science. The 2020 Nobel Prize in Physics was awarded in part to Reinhard Genzel and Andrea Ghez for decades of work establishing this result. The Event Horizon Telescope collaboration published the first direct image of Sagittarius A star in May 2022. A bright ring of glowing gas marking the photon sphere around a region from which light cannot escape. Not an inference, an image. Andromeda has its own central black hole. Its mass is estimated at between 100 million and 200 million solar masses, between 25 and 50 times larger than ours. This is inferred from the same method, measuring the velocities of stars and gas near Andromeda's center and calculating the gravitational mass required. The measurements have been refined over decades. Andromeda's central black hole is one of the more massive in the local universe, sitting at the heart of a compact and very bright nucleus. When the galaxies merge, these two black holes will eventually find each other. The process is slow. During the early merger, each black hole remains embedded in its own nucleus, separated by tens of thousands of light years. As the galaxies interpenetrate and the merger proceeds, dynamical friction acts on the nuclei themselves. Each nucleus is a concentrated mass moving through the background stellar population of the combined system, and that background star's drag acts to decelerate it and pull it toward the gravitational center. Over tens to hundreds of millions of years, both nuclei sink inward. the black holes converge. At some point, the two black holes are close enough that they form a gravitationally bound binary. Two objects orbiting their common center of mass at a separation that shrinks over time as they radiate energy in gravitational waves. The energy loss through gravitational wave emission is tiny at large separations, but becomes significant as the orbit tightens. The binary spirals inward. The final merger, when the two event horizons come together and the two black holes become one, releases a burst of gravitational energy that propagates through spacetime across the universe. Gravitational waves were predicted by Einstein in 1916 as a necessary consequence of general relativity. They are distortions of spacetime that propagate at the speed of light, carrying energy away from accelerating mass configurations. Two black holes orbiting each other are among the most powerful gravitational wave sources in the universe, because their masses are large and their orbital velocities near merger are a significant fraction of the speed of light. The first direct detection of gravitational waves came in September 2015, when LIGO detected a signal lasting less than a second, produced by the merger of two black holes of roughly 30 solar masses each, 1.3 billion light-years away. The peak power output during the final fraction of a second of that merger exceeded the combined electromagnetic luminosity of every star in the observable universe. All of it was released as gravitational waves. LIGO detected the resulting distortion of spacetime, a change in the length of a 4-kilometer interferometer arm 20 times smaller than the diameter of a proton. The measurement is real. It has been replicated dozens of times since. The supermassive black hole merger in Milkomeda will produce gravitational waves at lower frequencies and vastly larger amplitudes. This frequency range, nanohertz to millihertz, is beyond the sensitivity of ground-based detectors like LIGO, but within the target band of the planned LISA mission, the Laser Interferometer Space Antenna, a space-based gravitational wave observatory approved by the European Space Agency and targeting launch in the mid-2030s. LISA will consist of 3 spacecraft in a triangular formation, connected by laser beams millions of kilometers long, capable of detecting the tiny distortions in spacetime produced by supermassive black hole mergers across billions of light years. When those events happen in other merging galaxies, we will hear them. We are building the instruments to listen to the same process that will eventually transform the heart of our own galaxy. After the Milkomeda black holes merge, the product is a single supermassive black hole of roughly 200 million solar masses. It will feed on the gas funneled inward by the merger and on the stars scattered into vulnerable orbits near the center. When a supermassive black hole feeds actively at a high rate, the result is a quasar, an accreting black hole system so luminous that it outshines every star in the galaxy combined. Quasars were the dominant power sources in the early universe, when galaxy mergers were more common and more gas-rich. The merger of the Milky Way and Andromeda will recreate those conditions, on a modest scale, in the local universe. How bright the quasar in Milkomeda becomes, and for how long it operates, depends on how much gas survives the starburst phases and eventually reaches the central black hole. The answers are constrained by the simulations, but not pinned down precisely. What we can say is that the conditions required for a quasar phase will exist, that we have observed quasar activity triggered by galaxy mergers in other systems, and that those same conditions will be met in Milkomeda. Now let's put this merger in the context of something larger still. The Milky Way and Andromeda are not isolated. They are the 2 dominant members of the local group, a gravitationally bound collection of approximately 54 known galaxies spread across roughly 10 million light-years. Most of the members are small, dwarf galaxies, satellite systems, faint companions. The Milky Way's largest satellites are the Large and Small Magellanic Clouds, visible from the southern hemisphere as detached fragments of the Milky Way's glow. Andromeda's principal satellites are Messier 32 and Messier 110, two compact elliptical galaxies that have been orbiting it for billions of years. When the Milky Way and Andromeda merge into Milkomeda, the fate of these satellite galaxies is mixed. Some will be absorbed into the new merged galaxy during the violent phases of the merger. Others will be scattered into wider orbits. The Large Magellanic Cloud, based on its current mass and velocity, may well have merged with the Milky Way before Andromeda even arrives. Simulations suggest it could fall in on a timescale of around 2 billion years, earlier than the first Andromeda encounter. If that happens, it will trigger its own starburst and its own dynamical upheaval in the Milky Way, a preview of the larger event to come. The third largest member of the local group, the Triangulum Galaxy, Messier 33, a smaller spiral roughly 3 million light-years away, may eventually fall into Milkomeda, though on a longer timescale than the initial Milky Way-Andromeda merger. The local group, in the very long run, is converging. Over tens of billions of years, all of its member galaxies will be drawn toward the combined gravitational center of Milkomeda and absorbed. The endpoint, a single massive elliptical galaxy containing all the stars of all the current local group members, sitting alone in an expanding universe. Alone is the key word, because beyond the local group, the universe is accelerating away from us. This was established in 1998 and 1999 by two independent teams, the High Z Supernova Search Team and the Supernova Cosmology Project, both studying the apparent brightness of Type 1 A supernova at large distances. Type 1 A supernovae are useful because they have a characteristic peak luminosity that can be calibrated and used as a standard candle, much the way Cepheid variables were used by Hubble. If you know how bright something is, and you measure how bright it appears, you get the distance. The expectation before these measurements was that the expansion of the universe should be slowing down. Gravity should be decelerating the recession of distant galaxies over time, the way a ball thrown upward slows as it rises. What the supernova data showed was the opposite. The expansion was accelerating. The distant supernovae were fainter than expected for a decelerating universe, meaning they were farther away than expected, meaning the universe was growing faster now than it was in the past. Something is driving this acceleration. It has been called dark energy, which is a name for an unknown. It makes up approximately 68% of the total energy content of the universe. It does not dilute as the universe expands, or if it does so far more slowly than matter or radiation. Its nature is genuinely unknown. Candidates range from a cosmological constant, a fundamental property of empty space with a fixed energy density, to dynamic scalar fields, to modifications of general relativity on large scales. None of these candidates is fully satisfying. The observations are settled. The explanation is not. The consequence of dark energy for the far future is this: the local group is gravitationally bound. The galaxies within it will not be carried apart by the expansion, but the expansion will carry everything else away. The nearby galaxy clusters, the Virgo cluster, 54 million light-years away, the Coma cluster at 320 million light-years, are already receding. In hundreds of billions of years, the recession speed of the galaxies beyond the local group will exceed the speed of light, not because they violate special relativity — objects cannot move through space faster than light — but because the space between us and them is growing at a rate that, accumulated over vast distances, exceeds any finite speed. There is no speed limit on the expansion of space. When a distant galaxy's recession speed exceeds light, no light from that galaxy can ever reach us again. It crosses a cosmological event horizon. It disappears from our observable universe, not destroyed, but unreachable forever. In approximately 150 billion years, all galaxies beyond the local group will have crossed this horizon. Milkomida will be alone in an otherwise dark, observable universe. Any observers remaining at that point, if anything can persist across timescales of 150 billion years, more than 10 times the current age of the universe, will look out at an empty sky beyond their own galaxy. The cosmic microwave background will have been redshifted to wavelengths far too long to detect. The distant galaxy population will be gone from view. The large-scale structure of the universe, the cosmic web of filaments and voids that currently stretches across billions of light-years, will be invisible. They will have no empirical basis for suspecting that the universe extends beyond their galaxy, or that it was once filled with hundreds of billions of other galaxy groups. We are alive at the moment when all of this is still visible. The universe is currently fully readable, to the extent that instruments and intelligence can read it. That window is open now, and it will not always be open. The evidence of the universe's structure, its history, its scale and age is available to us in this epoch. Whatever we fail to learn now, in this era of large telescopes and sensitive detectors and mature mathematics, will eventually become unlearnable, not hidden, erased by expansion. Now let's come back to the present, because the galactic merger is not purely a future event. The Milky Way is currently absorbing the Sagittarius dwarf galaxy. This small satellite, discovered only in 1994 because it is hidden behind the dense star fields near the galactic center, has been passing through the Milky Way on a tight, repetitive orbit for billions of years. Each passage through the disk strips material from it through tidal forces. The stars of the Sagittarius dwarf have been unwound into long streams that loop around the Milky Way, tracing the orbital path of the dwarf across multiple circuits of the galaxy. These streams have been mapped using data from large surveys of stellar positions and velocities. They are there, real. The Sagittarius dwarf is being consumed in real time, not in some future epoch. The Large Magellanic Cloud, 160,000 light-years away, is in a complex and probably terminal gravitational relationship with the Milky Way. The Magellanic Stream, a ribbon of gas pulled from the Magellanic Clouds by tidal forces, arcing across a significant fraction of the sky in radio wavelengths, is direct physical evidence of this interaction. The stream is real, it is mapped. The gas is really there, stripped from the clouds, testifying to a gravitational relationship that will not resolve peacefully. And the Milky Way itself was built from exactly this process. The halo of old stars surrounding the disk, with their distinctive chemical signatures and orbital characteristics that set them apart from disk stars, represents accumulated debris from earlier mergers, ancient galaxies that fell in billions of years ago, torn apart and scattered, their stars now orbiting in the halo as a reminder of what was absorbed. The Milky Way is not an original structure. It is an assembled one. The same process that will transform it into Milkomida is the process that made it. Here is where the story ends. Here is what I want you to take with you into the dark. 400 years ago, no human being knew that other galaxies existed. The word galaxy, in its modern sense, was not in anyone's vocabulary. The Milky Way was a river of light with no understood structure. Andromeda was a small cloud. The idea that the universe extended beyond what the eye could see, filled with structures like our own at staggering distances, was not even a question most people could formulate. In roughly 1 century, from Hubble in 1923 to van der Merel in 2012, we went from not knowing other galaxies existed to knowing when ours will collide with the nearest major one. 1 century against the 4.5 billion years of Earth's history and the 13.8 billion years of the universe's. We did this with no cosmic privilege. We are medium-sized social primates on a rocky planet orbiting an average star in a minor arm of an unremarkable galaxy. The universe had no obligation to be legible to us. It had no obligation to follow rules that creatures like us could discover. It had no obligation to emit light that carries information across billions of light years, or to have that information arrive at our instruments in a form we could interpret, or to have our instruments be sensitive enough to read it. And yet, all of that is true. The universe follows rules. The rules hold everywhere they have been tested. The light from Andromeda carries the same physics as the light from the Sun. The gravitational wave signal from a black hole, merger 1.3 billion light-years away, obeys the same equations as the gravity that keeps you on this planet. The universe is not parochial. It does not have local physics and distant physics. It has one physics, and we found it, and it works. The merger of the Milky Way and Andromeda is 4.5 billion years away. No one we can imagine will see it, but we know it is coming. We know when. We know what will happen to the spiral structure, to the gas, to the star formation rate, to the sun's orbit, to the black holes. We know what the sky will look like at each stage. We know what will happen when the black holes find each other. We know this because we live at the right moment, with the right instruments, with a mathematics mature enough to interpret what they collect. The Andromeda Galaxy is 2.5 million light-years away. Every second, it moves 110 kilometers closer. In the time you have been listening to this, it has moved several 100,000 kilometers closer. In 4.5 billion years, the encounter begins. The starburst ignites. The tidal tails sweep across a sky that no longer contains the Milky Way in any form you would recognize. The black holes spiral together. Milkomeda settles. The distant galaxies recede behind their horizons. The universe grows dark and quiet and vast. But right now, tonight, the light of Andromeda is crossing the sky outside. Light that left that galaxy 2.5 million years ago, before the human species existed, before the last ice age, before the first human language. It has been crossing the gap at the speed of light for our entire evolutionary history. And it is almost here. The galaxy that produced it is 110 kilometers closer than when it did. The investigation is ongoing. We are the species doing it. And the fact that the universe produced, on at least one rocky world, something capable of understanding its own cosmic situation, capable of measuring the approach speed of a galaxy and calculating the date of its arrival, is not a small thing. It is the most interesting thing I know. Now let's talk about where the Sun ends up. This is where the story becomes personal. The Sun currently orbits the center of the Milky Way at a distance of approximately 26,000 light-years in a region called the Orion Arm, a minor spur between two of the Milky Way's larger spiral arms. Its orbital speed is roughly 220 kilometers per second, and it takes approximately 225 million years to complete one full circuit of the galaxy. In the 4.5 billion years since the Earth formed, the Sun has completed approximately 20 of these orbits. It is thoroughly settled into the disk, in a region of moderate stellar density, in a part of the galaxy that has been hospitable to the development of a planetary system, and eventually to the chemistry and biology that produced everything reading or listening to this. During the merger, this orderly, circular orbit will be disrupted. The gravitational influence of Andromeda's stellar population, superimposed on the Milky Way's own changing gravitational potential, will perturb the Sun's trajectory. In principle, every star in the Milky Way will have its orbit altered. The question is by how much and in what direction. The honest answer is that we cannot predict the Sun's specific trajectory through the merger with precision, because orbital dynamics over billions of years are chaotic in the technical mathematical sense. Small differences in initial conditions propagate into large differences in outcomes. A tiny uncertainty in the Sun's current position and velocity, which is unavoidable at any level of measurement, translates into large uncertainty in where it will be 5 billion years from now. What the simulations give us is a probability distribution, a picture of where a star like the Sun, starting in a position like the Sun's, is likely to end up given the merger dynamics. The distribution is broad. In some simulation runs, stars starting in the Sun's region end up in the outer halo of Milkomeda, far from the luminous center. In others, they are drawn into the inner galaxy. In some, they end up in what is now Andromeda's territory. In a small fraction, they are ejected from the merged galaxy entirely, flung into intergalactic space by a gravitational slingshot interaction. The ejection probability is small. Most outcomes keep the Sun inside Milkomeda. But the range of outcomes is wide enough that no single narrative about where the Sun ends up is more trustworthy than any other. The Sun will be somewhere. We cannot yet say where. What we can say is that the merger will not end the Sun. The Sun burns hydrogen in its core through nuclear fusion, and that process is completely decoupled from galactic-scale dynamics. The Sun will continue fusing hydrogen for approximately 5 billion years from now, regardless of what is happening to the galaxy around it. But here is the complication. The Sun is not the constant star it appears to be on human timescales. It is slowly brightening, approximately 10% per billion years. In roughly 1 billion years from now, the Sun will be luminous enough that the increased energy input to Earth will heat the surface to the point where the oceans evaporate and the water eventually escapes to space. In approximately 5 billion years, the Sun will exhaust the hydrogen in its core, expand into a red giant, and engulf Mercury and probably Venus before shedding its outer layers and leaving a white dwarf. The Earth may survive this expansion as a scorched, waterless rock, or it may be swallowed. The physics of the late solar system is uncertain in detail. The death of the Sun and the first encounter with Andromeda occur on roughly the same 5 billion year timescale. This is not a conspiracy of timing. It simply reflects that we are living in the middle of the life cycle of both a typical star and a typical galaxy merger timeline. We are here, now, in a galaxy that still has enough gas and time to support living planets, before the first major merger that will disrupt that stability. That positioning is not guaranteed to be meaningful, but it is, at minimum, worth noticing. There is another thing worth noticing about the starburst that the merger will trigger, and it is something most accounts of this event leave out. The starburst will manufacture enormous numbers of new stars. Many of those stars will be Sun-like, main sequence stars of similar mass and temperature, burning hydrogen steadily for billions of years, warm enough to heat a planet in a habitable zone orbit to liquid water temperatures. These stars will form from the same compressed molecular gas that the merger forces together. They will be born in the same process that produces the brilliant blue massive stars. But they will outlive those massive stars by billions of years, settling into long, stable burning phases after the chaotic starburst fades. Around those new stars, planets may form. Rocky worlds condensing from the dust and ice and heavier elements in the collapsing gas clouds. Worlds that orbit at the right distance for liquid water. This is not guaranteed. Planet formation is a complex process with many failure modes. But the chemistry required for it is there. Carbon, oxygen, nitrogen, iron, silicon, all the elements needed for rocky planets and organic chemistry, distributed through the gas clouds by billions of years of prior stellar evolution. The merger that disrupts the solar system also creates the raw material for new ones. This is a point worth sitting with. The collision of the Milky Way and Andromeda is often described as catastrophic, as destruction on a galactic scale. That framing is not wrong, but it is incomplete. It is simultaneously one of the most creative events in the universe's repertoire. The starburst phases will likely produce more new stars than the Milky Way has formed in the past billion years. The stars that form in those bursts will have their own planets. Some of those planets may have their own histories. The merger is not a grave, it is a forge. Let's talk about what happens to the sky, because the changes to the night sky across the billions of years of this process tell the story more viscerally than any description of stellar dynamics or black hole physics. Right now, the Milky Way appears as a faint band of light crossing the sky. The combined glow of hundreds of billions of stars seen edge on from inside the disk. In a dark location, far from artificial light, it is genuinely beautiful. A subtle texture of light and shadow, brighter toward the galactic center, studded with clusters and divided by dark lanes of dust. It has looked roughly like this for the entire span of human existence. Every human civilization that has ever stared up at the night has seen this same structure. Approximately 3.75 billion years from now, the sky will be different. Andromeda will have grown. Not dramatically, not yet, but visibly to careful observation. The faint smudge will have become a structure, a broadening of light in one region of the sky. Over the next hundreds of millions of years, as the approach continues, Andromeda will spread further. Its disk will become apparent. Its dust lanes will be visible with the naked eye. Its nucleus will be bright. On a moonless night in a dark location, the sky will contain, unmistakably, two galaxies. At the moment of first encounter, 4.5 billion years from now, the sky will be transformed in ways that would be unrecognizable to any human observer from our time. The tidal tails of stars drawn out from both galaxies will arc across the sky in great sweeping structures of light. The combined brightness of both galactic centers will illuminate the night. New stars, born in the starburst regions, will create brilliant knots of blue light visible to the naked eye. The Milky Way's familiar band will be distorted, warped, its edges blurring into the tidal material of the encounter. Over the following billions of years, through the second encounter and into the final coalescence, the sky will continue to transform. The two distinct galaxies will lose their separate identities, merging into a single brightening structure. The organized disk of the Milky Way, the flat plane of rotation that defines its shape, will gradually dissolve into the spherical distribution of stars that defines an elliptical galaxy. The night sky for anything alive on a planet in the outer regions of Milkomeda will be dominated by a diffuse, bright ellipse of light covering a significant fraction of the visible sky, brightest at the center, fading gradually toward the edges. There will be no Milky Way band, no distinct Andromeda smudge, just Milkomeda, spread across the sky in every direction, glowing with the light of 1 trillion stars that used to be two separate things. Whether any minds will be present to see any of this is a question we cannot answer. The timescales involved are so large that extrapolating biological or technological evolution across them is not meaningful. Life on Earth has existed for 3.8 billion years, complex animal life for 600 million years, tool-using humans for 3 million years, technological civilization for perhaps 10,000. The first Andromeda encounter is 4.5 billion years away, more than 1,000 times the entire span of complex animal life on Earth. What, if anything, 1,000 times the span of animal evolution produces is genuinely beyond our ability to say. What we can say is that the merger does not, by itself, eliminate the conditions for life. After the starburst phases end and the chaos settles, Milkomeda will be a stable gravitational environment. Stars will continue to burn for billions of years after the merger. Rocky planets will continue to orbit in habitable zones. The long, quiet, burning phase of a stable elliptical galaxy, cool, slowly fading, with very little new star formation, may in fact be more hospitable to the long-term persistence of life than the current Milky Way, with its ongoing stellar nurseries and occasional supernova and energetic events. The threat from the merger itself is concentrated in time, in the starburst phases and the active galactic nucleus. After those pass, Milkomeda is quiet. The most significant threat to any life in the inner galaxy during the merger would be the quasar phase, the period when the merged central black hole feeds actively on infilling gas and stars, blasting the surrounding region with ionizing radiation. How intense this phase becomes and how long it lasts depends on how much gas reaches the center. The zone of severe radiation hazard around an active galactic nucleus can extend for thousands of light years. The inner galaxy, during the quasar phase, would be inhospitable to complex life, but the inner galaxy is a small fraction of the total. The Sun's current position, 26,000 light-years from the galactic center, is well outside any plausible radiation hazard zone for Sagittarius A star in its current, relatively quiet state. A comparable position in Milkomeda, in the outer disk or halo, far from the active center, would likely be survivable through the quasar phase. Whether anything will actually be there to survive is a different question entirely. The honest position is this: we do not know whether the Milky Way currently contains any life beyond Earth. We do not know whether life is common or rare in the universe. We do not know whether intelligence and technology, once they arise, tend to persist for long timescales or tend to collapse or stagnate. The Fermi paradox, the observation that despite the vast number of stars and the age of the universe, we have detected no unambiguous signal of extraterrestrial intelligence, is a real and unresolved puzzle. If the universe is full of intelligence, then Milkomeda may well be inhabited by something when the merger occurs. If intelligence is rare or short-lived, Milkomeda may be as empty as the Milky Way appears to be today. Either answer is interesting. Either answer changes the significance of the merger in a different way. let's also talk about the instruments being built right now to study these questions and advance our understanding of everything discussed in this investigation. The Gaia satellite, launched by the European Space Agency in 2013 and still operating, has mapped the positions, distances, and motions of over 1 billion stars in and around the Milky Way with a precision that exceeds anything previously available. Gaia data have revealed the detailed structure of stellar streams from absorbed dwarf galaxies, constrained the mass distribution of the Milky Way's dark matter halo, and provided the most accurate available measurement of the Sun's orbit around the galactic center. The Gaia mission continues to accumulate data, and its final data releases will further refine our understanding of the Milky Way's dynamics. The Vera C. Rubin Observatory in Chile, completing construction and beginning its main survey operations, will photograph the entire southern sky every few nights for 10 years. In that decade, it will detect billions of galaxies, track transient events, including supernova and asteroid encounters, and build a dataset of unprecedented depth and temporal coverage. For the study of galaxy mergers, the Rubin Observatory will provide thousands of new examples of interacting galaxy pairs at various stages of merger, adding to the dataset against which our simulations of the Milky Way-Andromeda merger are validated. The James Webb Space Telescope, launched in December 2021 and now operating at the L2 Lagrange point beyond Earth's orbit, can observe galaxies in the early universe, galaxies as they appeared when the universe was less than 1 billion years old, with a resolution and sensitivity that reveals individual star-forming regions in objects previously known only as faint points of light. For the study of the cosmic merger history of galaxies, Webb provides direct observations of galaxies in their early, actively merging phases, informing the models of how galaxies assembled over time. The Square Kilometre Array, a radio telescope network spanning southern Africa and Australia, and currently under construction, will survey the radio sky at a sensitivity and resolution orders of magnitude beyond its predecessors. It will detect neutral hydrogen gas in galaxies across billions of light years, map the Magellanic Stream in unprecedented detail, and search for the signatures of active galactic nuclei in distant merging systems. And LISA, if it proceeds as planned, will open the gravitational wave window to the low-frequency universe where supermassive black hole mergers radiate. Every detection of a supermassive black hole, binary, spiral in and merger in another galaxy will be a data point informing our understanding of what will eventually happen at the center of Milkomeda. We are not waiting. We are building and measuring and refining across every wavelength of the electromagnetic spectrum, and now across gravitational waves as well. The understanding of galaxy mergers has advanced more in the past 2 decades than in the previous century. It will advance more in the next 2 decades than it has in the previous 2. The picture is becoming clearer every year, and the picture shows this: 2 galaxies falling toward each other across 2.5 million light-years, a collision in 4.5 billion years, a starburst that will create millions of new stars, 2 supermassive black holes that will eventually find each other and merge, a new galaxy, larger and older and quieter than either of its parents, settling into the long, slow fade of an elliptical old age, the distant galaxies receding behind their cosmological horizons. Milkomeda, alone, in an expanding darkness. And in this moment, right now, tonight, in the universe as it is, the light of Andromeda is crossing the sky outside. It left that galaxy 2.5 million years ago. it has been crossing the gap at 300,000 kilometers per second for the entire span of our species' existence on this planet. And the galaxy that produced it is 110 kilometers closer than when it did. That is the most interesting thing I know. Now there is one more layer that almost no discussion of this merger reaches. And it is the layer that changes the emotional register of everything else. The universe has a shape. Not a shape you can see in the conventional sense, but a shape in the way a landscape has a shape when you look at it from high enough. The large-scale structure of the universe, the distribution of matter on the largest scales we can observe, is not uniform. It is not a smooth, homogeneous spread of galaxies evenly distributed through space. It is a web, a cosmic web of filaments and sheets and nodes with enormous empty voids between them. This structure was predicted by the theory of cosmic inflation and gravitational structure formation, and it has been confirmed by the large-scale galaxy surveys of the past 30 years. The Sloan Digital Sky Survey, the 2 EDF Galaxy Redshift Survey, and their successors have mapped the positions of millions of galaxies across billions of light years, and the pattern that emerges is unmistakable. Galaxies cluster along filaments. Filaments intersect at massive nodes where galaxy clusters sit. Between the filaments are voids, regions hundreds of millions of light years across that contain very little matter. The Milky Way and Andromeda sit in the local group, which itself sits on the periphery of a larger structure called the local supercluster, or Virgo supercluster. The center of the Virgo supercluster is the Virgo cluster, a large galaxy cluster approximately 54 million light-years away, containing thousands of galaxies. The local group is a relatively minor component near the edge of this supercluster. In 2014, a team led by astronomer R. Brent Tully published a paper in Nature redefining the scale of the structure we inhabit. Using data on the motions of tens of thousands of galaxies, they mapped the boundaries of what they called Laniakea, a Hawaiian word meaning immeasurable heaven. A supercluster of galaxies stretching approximately 520 million light-years across and containing a mass equivalent to 100 quadrillion suns. Laniakea includes the Virgo supercluster, the Hydra Centaurus supercluster, and several other structures previously thought to be separate. We live in a suburb of Laniakea. The Milky Way and its collision partner Andromeda are 2 galaxies in a supercluster 520 million light-years across. And Laniakea itself may be part of a larger gravitational basin of attraction centered on the Shapley supercluster, even farther away. The Shapley supercluster, named after astronomer Harlow Shapley, is the largest known concentration of mass in the observable local universe. It sits approximately 650 million light-years away in the direction of the constellation Centaurus. It contains dozens of galaxy clusters and tens of thousands of individual galaxies. Its total mass is so large that it exerts a measurable gravitational pull on everything in the local universe, including the Milky Way. We are falling towards Shapley, slowly, as part of the larger flow of matter in our cosmological neighborhood. The Great Attractor, the mysterious gravitational anomaly that confused astronomers in the 1970s and 1980s, pulling our galaxy and hundreds of others toward a point in the sky hidden behind the zone of avoidance, is now understood to be the combined gravitational influence of the Norma cluster, the Hydra Centaurus supercluster, and ultimately the Shapley supercluster beyond. We are part of a flow of galaxies toward a structure 650 million light-years away. In the context of that flow, The local collision of the Milky Way and Andromeda is a small event in a much larger story of cosmological structure. But it is our small event, and it is the one happening on the timescale closest to our own reckoning. There is one more thing to say about the experience of living inside this story, and it is something that science is particularly good at producing in people who sit with it long enough. The collision of the Milky Way and Andromeda is often described as one of the most dramatic events in the future of the universe. And it is. But there is something more quietly dramatic about the fact that we know about it at all. Consider what was required. The universe had to be governed by consistent laws of physics, laws that hold equally in the Milky Way and Andromeda, and in the space between them. Light had to carry information accurately across 2.5 million light-years without being destroyed or corrupted. That information had to arrive at a planet orbiting a star in a suitable position for life to develop. Life had to develop, a process whose origin we do not fully understand and whose prevalence in the universe we do not know. Intelligence had to evolve, another process whose underlying mechanisms and evolutionary drivers remain partially uncertain. Technology had to be invented, telescopes had to be built, the relevant mathematics had to be developed. The specific measurement of Andromeda's lateral velocity had to be made by the right instrument in the right decade. All of that happened. You are the product of that chain. And the information about the collision is in your head right now. This is not sentimentality. It is a precise description of how unusual the situation is. The universe has no obligation to produce things capable of understanding it. It is under no constraint to make its processes legible to the life that arises within it. And yet, the processes are legible. The physics is consistent. The light carries the information. The instruments are sensitive enough. The math works. When you look at the faint smudge of Andromeda in the sky, if you ever go to a dark place and find it, which you should, just to see it, you are looking at something that will one day merge with everything around you. The light in your eye came from there 2.5 million years ago. The galaxy that produced it is 110 kilometers closer than when it did. The encounter it is traveling toward is 4.5 billion years away. You will not be there for it. Neither will anything you recognize as human, in any form you could describe. But the atoms will be there. The iron in your blood, the carbon in your body, the oxygen in your lungs, these will be part of the Milky Way when the encounter begins, part of Milkomeda after it ends, scattered through the starburst regions, maybe incorporated into new stars, maybe into new planets, maybe into whatever comes next. The universe is not static. It is in motion in every direction at every scale. The stars are burning. The galaxies are moving. The dark matter is flowing. The dark energy is accelerating the expansion. The supermassive black holes are waiting for their moment. The Andromeda galaxy is falling toward you at 110 kilometers per second. And you are here for the window of time when all of this is knowable. When the instruments are good enough, the mathematics mature enough, the evidence still close enough to read. This window will close, not soon, but eventually. The expansion will take the distant galaxies beyond reach. The evidence will be erased. The universe will become less readable with time, not more. We are in the readable era, right now, tonight. The investigation is ongoing. We are the species doing it, and the most important thing that investigation has produced is not the date of the collision, or the fate of the black holes, or the structure of Milkomeda. It is the knowledge that we are inside a universe that can be known, that the light carries the information, that the math works, that the instruments are sensitive enough, that the question can be asked and answered. That is the most interesting thing I know. Let me come back to one final detail before we close. One thing that the science of this merger reveals that almost no popular explanation pauses to appreciate. We have been talking about Andromeda as though it is a single thing, a galaxy, an object. But Andromeda is more than 1 trillion stars. It is 1 trillion stars each with their own history of formation, each burning through their own fuel at their own rate, each potentially orbited by their own planets. The Andromeda Galaxy, at the distance of 2.5 million light-years, appears to us as a smudge. But if you could be close to it, close enough to see the individual stars the way we see our own neighborhood, it would look like a Milky Way, a disk of stars, a spiral structure, a galactic center, arms reaching outward, star-forming regions, ancient globular clusters, gas clouds condensing into new suns, and at its center, that supermassive black hole, 100 to 200 million solar masses. Quiet now, as ours is quiet, but carrying the same potential, the same capacity to blaze when fed. The two galaxies are, in important ways, each other's counterparts. Neither is exceptional. Both are among the larger spiral galaxies in the local universe, but not among the largest in the broader universe. Both are approaching middle age in stellar terms, old enough to have mature populations of long-lived stars, young enough to still be forming new ones. Both are embedded in dark matter halos, whose masses are uncertain but substantial. Both carry at their centers the kind of object whose ultimate origin and physics we still do not fully understand. They have been falling toward each other since before the Earth existed. The gravitational attraction between them has been operating continuously, unchanging, for 4.5 billion years of the Earth's history. In that same time, the Earth went from a molten, lifeless rock to a world covered in oceans and land, populated by billions of species, orbited by satellites of its own making. Humans emerged and developed language and agriculture and science and spacecraft. We looked at the smudge in the sky and called it a cloud. Then we looked more carefully and discovered it was a galaxy. Then we measured its speed of approach. Then we calculated when it would arrive. All of that happened in the time the two galaxies have been falling toward each other, during what is still only a small fraction of the total time before they meet. The approach continues. The gap closes. The encounter approaches. The universe unfolds on its schedule, indifferent to whether anything is watching, completely legible to the things that are. That is where we are. That is what is happening right now. That is the story you fell asleep to tonight. One more thought, and then we are done. The Milky Way has been home to something remarkable. It has, in one small corner of one minor spiral arm, produced a species capable of wondering where the galaxy is going. That species built telescopes. It developed mathematics. It sent instruments into space and measured the lateral motion of a galaxy 2.5 million light years away and calculated what will happen to it in 4.5 billion years. All of that happened in approximately 100 years out of the 13.8 billion years the universe has existed. In 1/10 of 1/10,000,000th of the universe's age, the Milky Way produced something capable of understanding its own fate. We do not know if this has happened elsewhere in the galaxy. We do not know if it is happening in Andromeda. We do not know if it is common in the universe or whether we are the only ones who have ever asked these questions. The Fermi paradox remains unresolved, the sky remains quiet, and the silence, in the context of what we know about the scale of the universe and the age of the stars, is itself a mystery that deserves more attention than we can give it tonight. But here we are, asking the questions, finding the answers, measuring the approach speed of a galaxy, calculating the date of a collision, understanding the physics of starbursts and gravitational waves and dark matter halos and supermassive black hole mergers, naming the product of the collision Milkomeda and knowing what it will contain and how it will age. The Andromeda Galaxy is 2.5 million light-years away. It is moving toward us at 110 kilometers per second. In 4.5 billion years, the encounter begins. Everything we have ever called home will be transformed beyond recognition. And we know, we actually know, that is the most extraordinary thing about this story. Not the scale of the collision, not the billions of years involved, not the trillions of stars, or the supermassive black holes, or the gravitational waves that will ripple through space-time. The most extraordinary thing is that the universe, against all probability, produced something small enough to live on a rocky planet and large enough in mind to understand what the universe is doing around it. Sleep well. The investigation continues. The gap between us and Andromeda is 2.5 million light-years. Every second, it shrinks by 110 kilometers. By the time the room is light again, and whatever comes after tonight begins, the Andromeda Galaxy will be measurably closer than it is right now. Not by much. Not by any amount a human instrument could detect in a single night, but by 110 kilometers per second, across every second of every hour of every day that passes. The approach continues. It does not stop. It does not pause. It has not paused in 4.5 billion years. In cosmological terms, the appointment is close. You are inside the story.